Hello, welcome to today's session of NICER 201 online course on causal inference from observational studies. CAUSE. In this session, we'll discuss about causal modeling in observational study. This session is divided into two parts. In the first part, I'll talk about the statistical modeling based approaches to address confounding. And in the second part, we'll delve a little bit more on the practical steps where we compare predictive versus causal modeling. So, the first session, we talk about statistical modeling based approaches to address confounding. In inferential statistics, we use mathematical equations to understand the relationships between the exposure and the outcome and the various covariates that may or may not influence both the exposure and the outcome. And for the purpose of causal inference, we make certain assumptions regarding the probability distribution of our exposure and outcome variables and the various properties. Generally, it is seen that these assumptions hold good when we are doing randomized trials, wherein we resort to randomization of the intervention between multiple groups. However, when we do observational epidemiological studies, it is possible that these assumptions may not be fulfilled. Further, statistical methods also model the uncertainty in estimating the various causal parameters. Most of the all the statistical methods, in fact, only model for random error and ignore what is known as systematic errors or bias. There are various modeling strategies for estimating the causal effects in observational studies. If you look at literature, you will find any one of these three strategies that are generally seen in the current literature. The first strategy is called the adjust all strategy, wherein we adjust for all the covariates that are known to cause either the exposure or the disease or outcome or both. The second strategy is the predictor selection strategy, wherein we select covariates on the basis of some measure of their ability to predict the outcome or the exposure or both, given other covariates. Third measure or the third strategy to control for confounding and to estimate causal effects is known as the change in estimate strategy, wherein we select covariates based on the change in the exposure effect estimate, that is the change in, say, the odds ratio or the risk ratio or the rate ratio, given other covariates in the model. Let us look at each of these strategies in more detail and what could be the potential problems in using any one of these strategies while estimating the causal effect, specifically in observational study. When we look at the adjust all strategy, this strategy can identify several covariates which may be sufficient for confounding. However, there may be certain practical problems arising while using this strategy. It is possible that the set of covariates that are identified through this strategy may be more than adequate for controlling confounder in our study. And hence, that can lead to a problem in subsequent analysis in terms of either a problem with sparse data because now you have too many covariates to adjust for, and hence the power to estimate an effect from one covariate, between one covariate and or between your exposure and the outcome is reduced. There could also be a problem of multicollinearity because there may be multiple covariates which are correlated to each other and hence again can lead to the issue of sparse data. In fact, even the largest studies can become relatively small compared to the number of covariates that may be selected based on the adjust all strategy. And hence, such models may not in fact fulfill the goodness of fit criteria, which is more often used to assess whether a certain model is appropriate for fitting the outcome and the exposure relationship. Finally, and most importantly, even though a large number of covariates may have been selected, all of them may not essentially fulfill the criteria for confounder that we have discussed in the previous session. The next strategy is called the predictor selection strategy for confounder control. Here, we select covariates for control or addressing confounders based on significance testing. Most commonly, we use stepwise regression, where the goal is to have a parsimonious prediction of the outcome and ultimately achieve a goodness of fit of the model based on exclusion or inclusion of covariates in the model. The covariates that can statistically explain are associated with the most observed disease or exposure variation, or those who are most statistically significant with the small p-value, need not always be the same as the covariates that are important in terms of controlling for confounding. Usually, it is seen that use of this strategy leads to an overstatement of the significance of association of the covariate with the outcome, wherein we get very small p-values or narrow confidence intervals than what the actual true association may have been. Again, there may be the set of variables or covariates that are selected for control of confounders and are selected as potential confounders may not essentially fulfill the criteria for being a confounder. Finally, it is possible, if not taken into consideration, that multiple covariates which are related to each other may be selected, and hence the problem of multicollinearity and again sparse data could creep into this criteria for confounder control. Finally, there is the third criteria, which is known as the change in estimate strategy for confounder control. This is considered to be a superior strategy for confounder control vis-a-vis the adjust all strategy or the prediction selection strategy. Here, we test whether the change in the exposure effect estimate or the change in, say, the odds ratio or the risk ratio or the rate ratio after controlling for certain covariates, is that change bigger than a certain size that we predefine. This is looked at by comparing the percentage change in point estimate, that is change in the point estimate of the odds ratio or the risk ratio or the rate ratio, or more recently, people look at percentage change not just in the point estimate but in the confidence limits, the lower confidence limit and the upper confidence. Many a times this value is taken as 10%. There's no rule about that 10%, but most commonly it is seen in literature that a 10% change in the odds ratio or the risk ratio, or a 10% change in both the lower and the upper confidence limits can signify that this is the appropriate covariate which should be adjusted for as a confounder. However, there are certain concerns again related to this strategy. There may be more than one set of covariates that may be appropriate for confounder control, and hence only one set of covariate that is identified through this method may not be fully appropriate. It is possible that the change in estimate that we are seeing is not necessarily true change, but it's only because of non-collapsibility of either the odds ratio or the rate ratio. Also, we need to keep in mind which is the appropriate measure of effect under different conditions, whether is it appropriate to use a risk ratio or an odds ratio or a rate ratio when we are trying to look at the change in the exposure effect estimate. Again, whether to use a relative measure of effect, which is like a ratio measure, or an absolute measure of effect such as risk difference or attributable fraction, would also be important to understand the public health importance and the appropriate selection of the confounders for the particular exposure and outcome relationship. Here, confounding assessment is based only on the data that is analyzed, and so again there may be certain confounders that may be ignored, or even those covariates that are selected as confounders may not always fulfill the criteria for being a confounder. We will talk about how practically to deal with developing models to assess the causal effect in the next session. Thank you.